what happens when you put together fermionic and bosonic oscillators, and you can get these interesting operators that connect fermionic and bosonic, and I'll end up trying to explain kind of what the relation that the way in which the Dirac operator is, and the way in which the Dirac operator is kind of a square root of the usual Hamiltonian for a free particle, and what the relationship is between these kind of this idea of supersymmetry, which I talked a little bit about. Okay, so that's the plan for today and for next time. And then starting next week, we'll start on kind of what next part of the class I really want to get to, and I'm trying to figure out what I may start with on next Tuesday is just kind of a little bit of an explanation of kind of the Lagrangian point of view of all this, which you normally see in physics courses, and what the relationship is between what we've been doing to the Lagrangian form, and also say a bit about path integrals. So that's kind of a different way of quantizing things, which I haven't been, which is kind of quite different philosophy than what I've been pursuing. So that's what I'll try to talk about next week, and I'm trying to decide. I may also say a little bit about if I get a little bit farther into path integrals and explain kind of what you really need to do to kind of make path integrals well defined, but I'm not quite sure I want to get into that. And then after that, next week we'll get started in the next part of the class, which is more about quantum field theory, which is kind of, but I want to, what I'm going to do today, where I'm hoping to end up today, is to kind of explain, what the simplest version of the Dirac operator looks like, and to explain a way of thinking about the free particle and solutions to the free particle with spin. And one reason for kind of going over that in a lot of the way I'm going over it, I'll try to explain, is that later on, in and of itself, the free particle is not that complicated, that interesting thing to spend so much time on. But I want to kind of set things up in a certain way so that later on, when we do quantum field theory, it's you'll have the facts you need about what about the free particle in order to kind of to talk about quantum field theory and kind of how you deal with arbitrary numbers of free particles. So that's kind of where we're going next week or two. Okay. Okay. So let me get started on get back to where we were yesterday. So where we were last week. So we put together the put together the fermionic and the bosonic oscillator. So what I've done is I created a state space H, which was a bosonic oscillator, which you can think of as being that state space is given by the polynomials in Z1 to ZD, or you can also think of that as the what I call the symmetric tensor algebra. It's you take tensor products of copies of C D. So this is number of degrees of freedom, and you take all the various possible tensor products of this, but then you just look at the symmetric part, and you use the fact that the polynomials of degree the polynomials correspond to this. The polynomials on a vector space V correspond to this symmetric tensor products on the dual. But anyway, but there's this, and then I want to. So this is just the standard story about the bosonic oscillator, and I think I'll say some more about it next time. But the other thing is that you do the same thing for the fermionic oscillator, and that's really you're just starting with the same phase space, but you're doing you're quantizing. You're doing this fermionic quantizing, and your annihilation creation operators now have anti-commutation relations instead of commutation relations. But so this was the standard story you're used to. This was the story I did before. And last time I started talking about what happens when you if you try and put these things together. And then what happens? So I thought that in order to not make this too complicated, I want to first take the case d is equal to 1, and just think about what happens when you get d is equal to 1. And then when you quantize this thing, you're going to get operators, that kind of bosonic annihilation and creation operators, just the standard story of the harmonic oscillator in 1 degree of freedom. And here you're going to get fermionic annihilation creation operators, and these things obey the AB the identity and these. So the only difference really is between commutators and anti-commutators. But this causes these things behave differently in the sense that then they're nilpotent. Okay. So if you start anyway, if you start repeatedly applying these to a state, you only you get kind of the Pauli principle that you can only hit this thing, hit a vacuum state with this once and get an occupation number of 1. If you can't, if you do it twice, you're going to get 0. Whereas here, these guys, bosons, you can have arbitrarily high occupation numbers. Okay, but now what happens now is that if you have H, so your Hamiltonian is then just the sum of the number operators here, which is A, B, dagger, A, B, and the number operator here. And so, I mean, I could put an arbitrary constant here, which is going to be the so that my quanta are going to carry some kind of energy, let's say omega, and I could put an arbitrary constant here, and then I just have these independent bosons and independent fermions. Each kind of quanta carries a certain amount of energy given by whatever numbers I put here and here. But if I put the same number here and here, and so I guess I should put, maybe let's put this, you put it in H, put the same number, so I have the same quanta of energy for the fermions and the boson. Then this thing acquires this kind of extra, there's this extra interesting behavior that this guy then actually becomes a perfect square. And you can write this guy. You can then define what is it? I did this last time. Q plus is this kind of quadratic thing, which is a mixture of fermionic and bosonic operators. So this thing, in some sense, adds a fermionic quantum and destroys a bosonic quantum, and then you have the adjoint of this, which is and then what you find, then there's a simple calculation. Then you find that these guys are, because these guys are nilpotent, these guys are also nilpotent. But the interesting thing you find is that if you take Q plus Q minus and square it, well, you're going to get the terms where you square these things are going to give you 0. But if you calculate the cross terms, you can have a Q plus Q minus. Yeah, so this turns out to be then anyway. But the cross terms are going to give you an anti-commutator of QB and Q plus and Q minus, but anti-commutator. Okay, that's going to be the cross terms here, and if you calculate that using these relations, you see that that's exactly the Hamiltonian. Okay. So
quick question.
Yeah.
Does the Bosonic and fermionic and adjoint operator commute?
Yeah.
Okay.
Yeah. So because these are independent. They're acting on different spaces. Yeah. So they can be. Yeah. Anyway, so this is the crucial story here. H is. Yeah, so this is where I kind of stopped more or less, and it's kind of the kind of very interesting new behavior of this system, and it's kind of crucial, yeah, that you put these together in just this way, that the Hamiltonian is now perfect square. Okay, and so what happens then is you get let me okay. So let me just say a couple things. Clean this up. Okay, so what you can do anyway. I think I won't go through this last time, but what you find is you get Well, let's see. Maybe let me, instead of going through the same, I mean, so last time I actually wrote out explicitly then the states of the oscillator that you get and how they're related by these operators. And so I think maybe just to quickly draw the picture again, I had something like you had two states. Anyway, so you had some lowest energy state, kind of 0, 0, 0, where you were both and this was at zero energy, where you had no bosons and no fermions, and then here you had kind of 1, 0, and 0, 1, and then 2, 0, and 1, 1. And anyway, and etc. So things came in pairs, and then what happened here is you had is that Q plus, is that the way it works? Yeah. So Q plus and Q minus are adjoints of each other and take you back and forth between these two states with the same energy. You do the same thing here and here. And then you actually have some special behavior here. That here, if you take the so since the Hamiltonian here acts as 0 in the 0 energy state, then what these guys do is they give you if you act with Q plus or Q minus on this guy, you get it doesn't take you to a different state, it takes you to 0. Okay. So in these systems that have this kind of supersymmetry, there's this kind of behavior. The behavior you get is that and states with non-zero energy. The fact that you have the square of the Hamiltonian, the square root operator takes you to a different state typically. And then if you do it twice, it takes you back, and you just get energy eigenstates. But if you but then the lowest energy state, because this guy gives you 0, this thing is not necessarily going to take you to a different state. It may just take you to zero. Okay, so that's the general picture for the simplest possible oscillator. Now, the fun thing you could do with this is you can actually then make a whole kind of, you can think of what you were doing is that you had taken just the simplest possible harmonic oscillator problem with the q squared potential, and you'd added this kind of fermionic piece to it. But you can generalize this to arbitrary potentials, to try to put arbitrary to not just the harmonic oscillator problem, but any kind of any kind of one-dimensional potential problem. And then what you find is that for very specific choices of potential, you can actually recover this supersymmetry. You can recover the fact that the Hamiltonian is a perfect square if you choose certain potentials. So let me explain how this works. So what we're going to do is let's consider H. So now what I'm going to do is I'm going to go back from the Bargmann-Fock picture where my states were like just polynomials in Z. I'm going to go back to the Schrodinger picture, and I'm going to take and think of these bosonic this bosonic part of it as being just L2 of R, just the usual functions of position space. Okay, and so when I was if I just talk about the harmonic oscillator, I can think of it as being its states as being polynomials in Z, or I can think of it as being certain functions on R, which are these Hermite polynomials times a Gaussian. Remember, just the states of. But I'm still going to put on a harmonic in the fermionic oscillator, and I want it to be lambda. So it's going to be here. It'll just be C2, but this is kind of lambda star, if you like, of C. This is so this is just the D is equal to 1 case, and so this C2 you can think of as being C plus lambda 1 of C, but that's C plus C. Okay, this is the degree 0 stuff, just the constants as usual, and this is the degree 1 stuff. But and if you want, anyway, so if you want to think of it, the analog, remember, of the Z's here I was calling them theta here. So this would be the thing, that have function. It's functions of anti-commuting variables 1 and theta. Okay, but what this so this is what we're gonna do the same thing we were doing before. Treat the fermionic oscillators the same way, but for the bosonic case, go back to the position space representation, and so we can talk not just about oscillators but about arbitrary potentials. Okay, and then what we'll do is now we'll define instead of defining the oscillators by 1 over square root of q plus IP. Okay. Use choose a function W of q, and then take AB is equal to 1 over square root of 2, and instead of q, take this to be the derivative of, and I guess we could think of this as being a function of q or a function of big Q, since q commutes with itself. So we can think of it as being this way, plus IP. And then you also have, wait, sorry, that's right. Yeah. And then so the usual harmonic oscillator is this W is the W function is just q squared over 2. So if I take the function just q squared over 2, and then its derivative is 2q over q is just q, and then I just get back this. But what I can do now is that I can pick more, see what happens if I pick more interesting functions. If I pick, for instance, this to be a cubic or to be a quartic polynomial or some higher order polynomial, then I can do the same. I can define kind of new oscillators, AB, with this this way, and I'm going to get anyway. So I'm going to get some new operators. But what we'll find is that I'm going to be able to do the same thing that I did before, which is to write the Hamiltonian as a perfect square. That's the idea.
So here the W could be any potential energy, right?
Yeah, in principle this could be anything. Maybe it's better if it's not a polynomial, then maybe it's gonna be hard to think about. But yeah, let's just say for now any
polynomial. So what about 1 over Q absolute value? So it's something like the diagram?
I don't know. Yeah. I'm not sure. I haven't thought much about this except for polynomials. So yeah, but in principle, you can try and see what happens for arbitrary functions and see. I mean, if it's not a polynomial, there's issues about how to make. I mean, you want to. Well, if it's a polynomial, then it's clear what this operator has to be. If it's not a polynomial, you have to worry about exactly what you mean by that operator. But anyway, and I don't want to get into that.
Thank you. Do we need to change P, or is P still the same?
No, P stays the same.
Okay.
So it's just yeah. So this part of it stays the same. Okay. Then what happens? Okay. So now what you do. So now you use the same. So you use the same definition. So you use so you keep the same Q plus is what was it? It was AB. You do the same thing. You keep the same. It's just the same. It's going to be the same kind of general structure as what's happening here, and Q minus. And then now what you can do then is you can then write choose. So then what you do is you then are going to create a system that is going to have a similar kind of behavior to this kind of thing, except just by defining the Hamiltonian. Choose H to be Q plus Q minus squared. Okay. So now it's the same story as everything looks kind of the same as before, except you've now got this guy is now this AB is actually something much more complicated. It doesn't have the same. This is not just the simple the usual simple annihilation operator for the standard harmonic oscillator. It's a much anyway. It's a more interesting operator. Okay, so then what you can do is you can then calculate what H is. So let's. So you can then calculate what H is in terms of Q and P, and then these fermionic, operators you haven't changed at all. So then the fermionic oscillator. So you take H, so this guy, then you start calculating what this is. Yeah. So it's going to be yeah. So anyway, if you start, so let me. Calculation is in the book in more detail, but let me just do this fairly quickly. So if you start squaring this thing, you're going to get a factor of W prime of Q plus IP, and then W prime of Q minus IP. That's going to be from the, and that's going to be for having a dagger F AF. Okay, that's from the yeah. Okay. Anyway, let me. Anyway, if you just write this thing out and start multiplying, you should get a factor that looks like that, and then another factor that looks like it looks like the adjoint of this. Minus IP. And then just the adjoint, the AF dagger. Okay. So if you work that out, and you get that, and then if you multiply these things out, you'll get a you're going to get a factor of a half W prime of Q squared plus P squared, and then this guy, but this guy, and then there's a half on the with the commutator you get a commutator term I P. And then that's gets multiplied by A F A dagger. Sorry, this the other way. Okay, it's that. And if I've done this right, so this guy now. This guy, the anti-commutation relation says that this guy is just the identity operator. So you get a half W prime of Q squared plus P squared. Okay. And this is just the standard harmonic oscillator term. If W prime of Q is just Q. If W of Q is Q squared over 2, then this is just a harmonic oscillator. But you also get this other term, which is going to be there anyway. Which is okay. Yeah. Anyway, you get this other term, and what does it look like? It's a half. Maybe a good way to say so. It's I times the commutator of P W prime of Q. And then, but now remember what this guy does. This is the thing which gives you, one on, you're on this in this two-state system, and this is the operator that gives you, one I guess on the filled state and -1 on the unfilled state. So this is really, you can also think of this as just acting on C2 on C2. This is just the third Pauli matrix. Okay, so this guy is just going to act as 1, -1, and 0, acting on, because your state space is just it's just C2. Okay, but now the trick then to this then is to realize that the operator, so what the operator P does, remember, especially if you multiply operator P by IP is just, in the this is the infinitesimal generator of translations. So it's just going to, so commuting with this operator is just going to, is just differentiation with respect to Q. So this guy, I guess the thing to say is that this guy is this guy here is really the same thing as just the derivative with respect to q of this guy. So it's w by q. And so altogether, what this thing is it's a hat. It's the usual guy plus p squared plus a half to sigma 3. Okay. So if the so what this looks like for the if w of q is just q squared over 2, the bosonic piece of this would just be the standard bosonic Hamiltonian, and then this would just be this would just be 1, and so you're so then you would just have this sigma 3 term, but that's exactly the standard kind of fermionic oscillator term that you have a half times this guy tells you about the energy difference between a no fermion and a fermion. Okay, but the interest. Okay, so this is the this is but the fun thing about this now is that this is equal to so if you pick an arbitrary polynomial w of q, and you've got and now we've got something which isn't an oscillator. It's kind of a very it's a standard kind of free particle term, and then some kind of non-trivial some kind of non-trivial potential of some kind, and then you've got a then you got this extra term, a fermionic term, and again, and if q is order. If w is of order more than 2, then you've got an interesting kind of coupling between the standard kind of fermionic Hamiltonian, and then it's got factors of q in it also. So it's an interesting system, but the kind of amazing fact about it is that it's actually a this guy is a perfect square.
So I have a question. So does the first term and the third term form together exponential? The two derivatives of the exponential.
Wait, which terms?
I mean, in the last line, the first last line, the very last line, the first term and the third term, do they form together a second derivation of the exponential?
An exponential? No, I mean I don't. Oh, I see. But it's different because this has got this has a sigma 3 in it.
So what about the exponential of something with sigma 3?
I don't know. Yeah, I mean I don't think that you can write this as yeah. I mean I don't know any reason. I can't immediately think why that should be true. That this shouldn't be this isn't intended to be a power series expansion of something more, of something. I mean, this is really all it is, and it's a square root. I mean, it's possible that this is a power series for something where things are nilpotent and you don't. But I haven't thought of it that way. Okay. Yeah, and as far as I know, it's just this, but the important fact is that it's is that you can actually write it. I mean, I guess I've erased anyway. If you go back and look at the definition of q plus and q minus, this operator is a perfect square, and so it's going to have the same kind of behavior.
I guess it's a derivative of like a unitary evolution operator or something. Like if you.
Well, it's going to be if you're going to. I mean, you can exponentiate that. You can exponentiate this. This Hamiltonian can be exponentiated, and that will give you your time evolution. But I'm just not. Yeah, I mean the fact that you're seeing a first order derivative here and a second derivative, I don't Yeah, I'm not. There may be a reason for that, about a longer story, but it's not the one I immediately am aware of right now. But yeah, so this will have the usual story. This is the infinitesimal generator of time translations, and so you can exponentiate this in principle. The thing which is kind of weird and really new is that it's this infinitesimal generator of time translations has a square root. So there's something very funny going on. One is your very kind of fundamental fact about symmetry and about the most basic symmetry of time translations. By moving into this fermionic world, you've created this newer environment in which what you thought was the simplest possible idea of how do I translate infinitesimally in time now has something much more complicated going on with that you can take a square root of it. But it's a very weird. It's not and we've in some sense accomplished this by moving from the story of Lie algebras to the story of Lie superalgebras. In some sense, but this is kind of the basic mathematical fact that if you're willing to kind of to go from Lie algebras to Lie superalgebras by putting in these fermionic variables, all of a sudden operators which you thought you understood very well, things like, and when we get to the Dirac operator, we'll see that the Dirac operator again is going to be in some sense a square root of a Hamiltonian or of a Casimir operator. So operators which you thought were your fundamental things you knew and understood all of a sudden pick up more interesting structure and square roots like this. Okay, so maybe let's see. So now one of the things you can do with this. Okay, so okay. So in principle, this now gives you all sorts of things to play with. You can pick your favorite W of Q, and then see if, and now you have a new quantum system, and it's a new quantum system with this weird extra symmetry, which you would never have expected before. And then there's different things you can do. But maybe one of the main things you can do is to find okay, so generically, then what you have, so in general, what you do is you have two states, okay, same energy, which is, if you take any psi, which is an energy eigenstate. Well, if you multiply it by h, you're just going to get back the same state times times the energy. But what you can do now instead is look at sorry, not zero. Sorry. So you get for each state like this, you can create this other state, and then since h is this guy squared, h commutes with this operator, and so this guy these two guys have the same energy, and generally they're different states. So what you've discovered is that this kind of structure that you created of having the Hamiltonian have a square root means that your states are going to occur in pairs. They're going to be paired. Your energy eigenstates are going to occur in pairs like this. But the problem, but one thing that can happen is and so in general, since if the energy, so these are different. Right? If the energy is not equal to zero. Okay. Oh, and one other thing to notice about this is, but because your energy is a perfect because this guy's a square, this also means that your energies are going to be positive also. But anyway, but something different though happened. So if the energy is non-zero, then these guys have to be these guys have to be different states. But if E is equal to 0, and so this is going to be your ground state, you can either have Q1 plus Q, that's right, is not equal to 0. Or so if this guy actually has energy 0, so that the square of this guy is going to have eigenvalue 0, then it's perfectly possible that this guy will just give you a 0. Okay, so and this is what happens in the the simplest fermionic oscillator that we talked about. There, the lowest energy state, there wasn't something else paired with it. It was just if you operated with this guy on this state, you didn't get another state, you got 0. So that's why, so the lowest energy state, all the states were paired except the lowest energy state, and that was a single unpaired thing. Okay, so now this thing, you can kind of, anyway, so you can do very simple-minded things with this, but maybe just kind of say one reason that people actually got very interested in this at one point, even though it's a fairly simple-minded quantum mechanical calculations. And the reason they got interested in it was that there was a question of, so you can say, if 2 is true, so you can think of this operator, which is the square root of the Hamiltonian, as a generator of a new kind of symmetry operation, the supersymmetry. So this is kind of just as the Hamiltonian generates the symmetry of time translation, its square root, this guy, is what you call what we call a supersymmetry operator. And remember that if a state is, if your generator of a symmetry acting on the state gives you 0, that means that you interpret that as saying that the state is invariant under the symmetry. Okay, so you can interpret this as being, the state 2 is that 0 is invariant under invariant under the supersymmetry. Okay. And this is just kind of an analog of saying if you're a infinitesimal generator, hitting a state means 0. It means that if you try and exponentiate it, you're just going to get 1, and it's going to be invariant. And if you say 2, 1, 0 is not invariant. Understand? Okay. And you say that, and then what you say is that the words are that is spontaneously broken. Okay, so what? This is a very, very baby example of a phenomenon that people are very, very interested in for other reasons, which is that if you've got a quantum state, and your quantum system is kind of built by taking some lowest energy state, which you can think of as kind of a vacuum state, and then hitting then the other states are what you get by hitting this with various operators. Now the higher energy states are going to have this kind of phenomenon. You're going to tell that you can have a supersymmetry because all the highest energy states are going to be doubled. Okay, but there's something funny can happen for the lowest energy state, and you can interpret it. If this happens, if the supersymmetry generator acting at the lowest energy state, doesn't give you zero, then you can think your kind of state which you're trying to think of as there being nothing there and being a perfectly kind of invariant structureless thing that you're going to build everything on. Instead, this actually has some structure. It's this vacuum, if you like. When you act on it with a supersymmetry, you move it. It gets moved to something else. Okay, and so that's the. So anyway, the terminology is just that if you have a lowest energy state and an infinitesimal generator of symmetry that acts on it and it doesn't leave that vacuum lowest energy state invariant, but changes it to something else, it means you in some sense have kind of a situation of degenerate vacua. You've got not just one kind of lowest energy state, but some structure, some differences, several different lowest energy states in a structure to them. And so you've got this something interesting happening in what you thought was your vacuum state, what was supposed to be a completely invariant thing. So that's what, and so what people were very interested in was this question of these sort of supersymmetric extensions of the theories that we already know. Where I think I said last time, where these are much more complicated quantum field theories, and you've got to and you can have these supersymmetries, which are the square roots not just of the Hamiltonian, but of all the generators of all the translation generators, and those theories, are very hard to kind of analyze what's happening in them. But one thing that they had the similar structure that you expected all the states to be paired, you expected all the non-zero energy states to be paired, unless but that argument, there would be a problem with that argument if this happened. So anyway, it was a big industry at the time, and in some sense still is, that people would like to know in these much more general supersymmetric versions of quantum field theories is the supersymmetry spontaneously broken or not? And the really nice thing about this thing I just wrote down for you is that you could, there was a very simple-minded version of that problem, which just came down to trying to understand this.
Two questions.
Yeah.
One is can we always somehow take the square root of any Hamiltonian?
No, yeah. So it's very special Hamiltonians, and you can see. So I kind of did this. I've now erased it, but that one that I calculated, I created that by telling you what this was and then by squaring it. So yeah, so it's a very special property, of Hamiltonians, and it requires also that you have fermionic variables. So you have to have bosonic variables and fermionic variables, and you have to have a very special Hamiltonian, and then you can get this to happen.
Okay. Another unrelated question is what symmetry could correspond to the supersymmetry?
Well, it's not a so in some sense it's just a, well, I've written down, so it's a, this guy here, I guess okay, so maybe let me say that. Yeah. Anyway, so it's, well, if you go back to, so here we're working with a representation of the supersymmetry, right? So it's not just, we've actually got states and operators. So we're actually, so this is actually, this operator is a representation of it. You should think of this guy as being kind of pi prime of something, except that this is now X is an element of a Lie superalgebra. And yeah, okay. So I'm associating, operators to these, yeah. So I mean, in some sense, the Lie superalgebra that we've got here, the Lie superalgebra we're playing with, is one that it's got this bosonic piece, which is these functions of p's and q's, and then it's got this fermionic piece, which is these psi functions, right? And the bracket is the standard Poisson bracket on the p's and q's, and then this this kind of plus bracket I wrote down on the sides. Okay, and so that it's within that big that big Lie superalgebra of these p's and q's and psi's, there's what I'm saying is that there's the Hamiltonian function, some function of the q's and p's, which is the Hamiltonian, is anyway, that thing is a square. That's the anti-commutator of two things, and that's so the anyway. I mean, this is all happening in some big Lie superalgebra, but the crucial thing is that this H, which is some particular function of the p's and q's and psi's, is it is a square. It's a plus or minus Poisson bracket of something with itself, and that's anyway, and so it's this guy, which you normally think of as being just a generator of a generator just of an R group of translations in your phase space. That R group has that's what has a square root. But the problem is there's not a group. You can't really think of the tricky thing about this whole Lie superalgebra picture is that when you exponentiate these fermionic things, or you exponentiate the analogs of these kind of fermionic x's here, you don't get a normal group. It's not like in the case of a Lie algebra, is you exponentiate Lie algebra elements, get Lie groups. If you exponentiate this Lie algebra element, and you get the group of time translations. Okay. So but the problem is that if you try and exponentiate things in a Lie superalgebra, you get an even harder to understand abstract thing called a Lie supergroup, and that's not so it's I don't know if that helps.
Like, I mainly asked that because I mean, I know of example of like spontaneous symmetry breaking where, like, let's say like the Mexican type potential, like that we could at least pinpoint like what are the symmetry breaking and how it breaks to like lower level symmetry group.
Right.
But you're saying in this case, like we have to, I guess, either dealt with the harder to understand Lie super group.
Yeah. So I mean, I'm kind of, maybe what I'm doing here is very bad. In that I'm telling you about a simplest example of spontaneous symmetry breaking. The example I'm giving you is is a version of a supersymmetry and superalgebra version. So it's actually harder to understand. What I think if you don't deal with you can say the same things that I said here, except not using supersymmetry, just using symmetry. So so there's a more general phenomenon that if your lowest energy state of your system, you've got some symmetry group. Let's say there's some UN group acting on your theory. Your Hamiltonian commutes with some UN symmetry group that acts on all the operators. You can have this exactly the same question. Does that UN symmetry, does it act trivially on the lowest energy state or not? Is the lowest energy state, is the vacuum invariant under this interesting UN group of symmetries? And if the vacuum is invariant under that, you say that it's anyway, it's just invariant. If the vacuum gets moved around under this interesting group of symmetries, like in you're thinking this Mexican half potential, you're sitting at the bottom of a non-trivial potential, and you can move around in it. That's kind of a simpler example of spontaneous symmetry breaking. That's not the super. The very special thing that's happening here, though, is that so you're not just working with symmetry. You're working with this. You're not just working with Lie algebra. You're working with superalgebra algebra and a representation of it. And but the thing which the new really weird phenomenon here is that this generator of your symmetry is a square root of time translations. Okay, yeah. So it's anyway. I can see why you're having trouble. Anyway, I'm telling you things kind of out of logical order. I'm telling you about a kind of exotic notion of what it means to have your lowest energy state have a spontaneously broken symmetry. It's an exotic supersymmetry version, whereas it might have been better to explain the non-exotic version first.
At least, is there some kind of visual way to understand this supersymmetry breaking, like the U1 case?
Yeah. I mean, the whole problem with this kind of these superalgebras is that they really aren't. Yeah, I mean, they really have this weird algebraic structure to them. I mean, they're kind of very natural algebraic objects, but the geometry. There are various attempts to try to think about supergeometry, and if you try and think about supergeometry, you start thinking about, well, let's think about the usual geometry, but let's also think about not just vectors, but some kind of infinitesimal vectors that that are going to be nilpotent if I square them. So you take the usual directions, and then you have some nilpotent directions in which the square of the coordinate is 0, and you try and think of a supergeometry. But it's both hard to visualize, and it's not. I don't think that doesn't help so much. But the algebra is kind of straightforward. Okay, let me.
Sorry, just a question of this supersymmetry. I'm still wondering, why is X part of the Lie superalgebra?
Well, just because it's just the square root. I should have actually tried to figure out what actually is it. Let's see. Well, let's do this. I'm not sure. Well, I'm not sure this is really going to help. But remember, so I had that. Okay. So So this Q plus Q minus is what AB AF dagger plus AB dagger AF. Right? Okay, but the point is, this is a quantization of something. Okay, and so this is an operator giving you anyway. This is a quantization of something. Quantization, and then it's something of. Because remember, what AB was something like 1/2. So here you have a 1 over square root of 2. So this is a quantization of some classical thing, which was something like W prime of Q plus IP, and then AF dagger. Remember, so I thought of an oscillator as quantizing some fermionic variables, which I called theta and theta bar. So this is, I guess, I don't know. I hope I forget which way I did this, but this is like theta bar, and then this is going to be plus over square root of 2 on a Q minus IP, and then theta. Okay. Right. So something like that. So in the anyway, so this is just some function on complexified phase space, Okay, so it's some complexified function of q's and p's, and it's a function of the thetas and theta bars. And the then you have to treat this function as being, you know, if you start manipulating this, you then just have to use the q p is equal to 1 and what is it, theta bar plus 1. Okay, so you want to take, well, anyway, so you want to take a plus or, yeah, you have to define a plus or minus super Lie bracket on the functions of q and p and theta bar that has this property. Okay, and then you extend it to any function, and so you're, in some sense, you're, before you did all this, you just had a nice story about the Lie algebra of functions of q and p, and the bracket it was the Poisson bracket. Okay, and then but if you put these together, now you've got function. You've got this exotic kind of Lie superalgebra, which has got generators q, p, theta, and theta bar, and it's got a Lie super bracket on it, which, among other things, has these properties. And the point is, within this whole mess, the fact that I set h, you know, so anyway, so you can write h is then going to be, I forget, it's going to be something, the same thing, plus or minus. It's going to have this kind of property. You're going to have the fact that the Hamiltonian is anyway, yeah. So this is I have to work out exactly what it is, but the fact that this Hamiltonian operator has a square root comes down to the fact that the Hamiltonian function is the super Poisson bracket of something with itself. I don't know if that helps.
Actually, I don't know why q and p are in the super Lie algebra, because a super algebra is something, you know, that is symmetric in with degree 1 stuff, right?
Symmetric. No. Well, I mean, so.
But Poisson bracket is anti-symmetric, and I don't know why q and p are in the super Lie algebra.
Well, okay, so remember, so the way you define a super Lie algebra, remember, is that it's something that you've got x, y, it's got a super bracket on it, which is which has this property that well, actually, so it's y x times, there's a minus sign, and then a minus 2x x, y. So if x and y are even or odd, yeah. So you have to do something different if x and y are the sums of even and odd things. But if x and y are even or odd things, and so these are even generators, these are odd generators. Okay. Then if x is something you get by multiplying these together and multiplying some of these together, if it's then a Lie superalgebra is something that that has a bracket on it, which behaves like this. So it's a generalization of what you had for I mean, so in the if you just have q's and p's, if there's no thetas and theta bars, then what happens is this guy, these are even, this is 0, and you just get that x, that the super Lie bracket satisfies that that you have a commutator. It's a commutator. I mean, sorry, it's not a commutator. It's anti-symmetric. And if you just have thetas and if you just have odd things here, just thetas involving thetas and theta bars, then you're going to get then you get a plus sign. You get a plus sign. But if you put these things together and you use these relations on generators, that you can create an interesting super bracket on functions of q, p, theta, and theta bar, and it's going to have this property. So it's going to be even or odd depending upon whether you're looking at the commutator of even things or odd things, or even odd, or odd, or even, or even odd. Does that help?
Yeah.
Okay. Yeah. I mean, it's a bit of an exotic story, but. Okay, so let me finish. I think looks like I won't get to the, just as well, maybe not get to the Pauli equation today, but let's, okay, so let's do a couple more things. So the nice thing about this is that you can find, let me get rid of this. So so you can find lowest energy states by looking for solutions. Oh, wait a minute, let me see. And so this is of type, what did I call it? Of invariant, let's see, invariant. Okay, so one way to think about this spontaneous symmetry breaking thing is to see, okay, let's look for invariant lowest energy states. Okay, let's look for supersymmetry invariant lowest energy states. They're going to satisfy this equation. Okay. And so I worked this thing out in the let me, since we're running out of time, let me just kind of write on, this is in the section 33.2. I work out what this equation says, and what you end up with is you end up with 1 over the square root of 2, 0, 1, minus 1, 0, and then a ddq minus the first derivative of q times, and I guess this could actually be a q, yeah, q, sigma 3. See, this could then be a q and sigma 3 applied to psi plus. So we're states, are they going to be two component things? They're going to have one. So they're going to be functions of q times c2. So they're going to have to be two component objects. Okay, and you want to you want to find solutions to this guy. Anyway, so this becomes just a very simple. You pick your w. And this becomes just a simple first order differential equation. You can and you can look for solutions. And what you find, and I guess maybe I could say this yet. So that this is so the solutions are e to the w of q. Yeah. So they're e to the w prime. E to the w of q sigma 3. So that's right. Times just some constant, some kind of initial values, if you like, some constants, so some arbitrary constants. I think I got this right. Yeah. Yeah. Okay. Okay. And so whether these things are so your problem, this is what the solutions are going to look like. Now for these to be legitimate solutions and actually give you a legitimate state, you need these to be normalizable. So this must be, you need C plus, C minus, such that these are in L2 of R. So your problem with your function is that, and with your, so the sigma 3 is going to be, is going to give you plus or minuses on this guy. If there's a plus here and a plus here, you're going to be it's going to be e to the, well, everything is going to depend upon the sign of W. So it depends on the sign of W of Q at plus or minus infinity. So you have to worry about, what is your polynomial do? What is your function of Q doing as you go off to infinity? If it's and for a typical polynomial, this thing, it's going to be blowing up, and it's going to either be blowing up to positive on each side, or negative on each side, or positive on one side, minus on the other side. So you can get all different possibilities, and you can find, it's easy to find examples where there are no solutions to this. So you can find the study of Q with no solutions. Oh no, sorry. Okay. Oh no. So sorry. I guess, how does it work? It works out. Yeah. So there exists W with no solutions. That's right. And so if you pick, the behavior infinity of this guy, so that there are no normalizable solutions to this equation, then what you've shown is that there are no solutions to this guy. So your lowest energy state cannot be an invariant state. It has to be one of these so-called spontaneously symmetry broken ones. Okay. So the argument is that even in this kind of simplest supercore mechanics thing, that by picking W of Q behavior properly, we can kind of create systems where this can happen, where the lowest energy state cannot be invariant under supersymmetry. The supersymmetry has to be spontaneously broken. So this is what the general argument. Okay.
What about harmonic oscillator? Like, wouldn't that exponential blow up?
Well, okay. So in a harmonic oscillator case, you can figure this out. So it's positive. Yeah. So what's going to happen? So this is going to always be positive. But remember, sigma 3 can be +1 or -1. So what you have to do is where it's +1, you just have to take C plus is equal to 0 and C minus is not equal to 0. Okay. And then the minus eigenvalue, the minus entry here will multiply the positive thing here, and you'll get something normalizable. Because remember, this depends. What happens depends on the sign of this guy at infinity. You get two possibilities here, +1 or -1, and then you can adjust these guys. But
then the exponential, we can express it as like cosine and sine. The cosine part, it's all positive. It's identity.
Okay, I'm sorry. Yeah, I have to. But the cosine, no, I mean, it's not a cosine and sine because it's
Professor, I think there is no trigonometric functions here.
Yeah.
But we only have one blowing exponential and one decaying exponential.
Yeah, I guess, I mean, maybe I should
so
say
we
this.
We just drop that blowing.
Yeah, exactly. So I think what it should be is that this is e to the W of Q 0, 0 minus W of Q, right? And that's so this is just e to the W of Q e to the minus W of Q, right? Is that right? So it's just yes. So we just have to choose. Anyway, I mean, as long as one of the if one of these is normalizable, then we just have to choose the choose the coefficients to make the coefficient to the non-normalizable one 0. But what can happen is that if W of Q is cubic, then remember then what it's doing is W of Q is going to is going to minus on one side and plus on the other side. So you can't get rid of the problem. If W of Q has the same sign as you go off to infinity on both sides, then you can solve this problem by choosing one of the coefficients here to be 0 and getting a normalizable solution. But if it's going off, if both of these are going off to W of Q is going to positive infinity on one side or the other, there's nothing you can do. There's no way to get a normalizable solution. Okay.
Okay, yeah, that makes sense.
Okay, let me just take a few minutes. Anyway, so this is, I mean, the real beauty of this is it's a very, it's very, very simple-minded. It comes down to very simple differential equations and stuff, and it's, yeah, but it provided, historically, it provided a really interesting kind of toy model for this question of what for people to think about what really is a supersymmetry and what does it mean for it to be spontaneously broken. But let me quickly tell you one big generalization of this, which and this is gonna. Sorry. Actually, maybe I should ask you. So how many of you have seen differential forms in the Duran differential? Anybody? 1, 2, okay. So you guys are going to have more of an idea of what I'm talking about. The rest of you have to trust me. So what you're doing is a generalization. So for d degrees of freedom, then what you do is you take H is L2 of RD, and then the star. Okay. So this is just our. I'm just doing the same thing I did to get away from the. I have a kind of a bosonic piece and a fermionic piece. And I've moved away from the Bargmann-Fock point of view on the state space to the position space representation here. Okay. So what this is you can think of so you can think of this as kind of these are functions on RD that take values in in this gadget, and this gadget is something that has a basis. Which so these are functions of Q1 up to QD, and here when you're tensoring this, you can also you can think of it as functions in here that are taking values in here. They're taking values in something as 1. And so I'm going to associate some to each Q. I'm going to associate some fermionic thing, which I'm going to call DQ, just because that's the notation that we use in geometry. DQJ, and then DQJ wedge DQK, DQ1 wedge DQD. Okay. So this is going to the notation that we use in geometry. So the point is that this gadget occurs in a course in differential geometry. You'll see this, and what you see is what are called these are called differential forms. And there are various ways of motivating this. It's actually kind of very hard to motivate very well in a geometry course, but in a geometry course, you often find that we've got differential forms, and sometimes you'll see it written as omega stellar of RD. Well, what it is it's functions, and then it's some function plus functions multiplied by dqj's plus function multiplied by dqj's times dqk's, where you put in a wedge to remind you that it's an antisymmetric product, and then you get up to here, and there's 2 to the, so this is a 2 to the, there's 2 to the d of these guys. So you've got kind of 2 to the d functions, which are, and they're called, and these are called differential forms. And these are said to have degree 0. So this is the ones that, so this is omega 0 is just functions. Omega 1 is functions that just have 1 dqj in them. Omega 2 is the ones where you've got 2, etc. Okay. Okay, so these are differential forms. Now the nice, the 2 kind of facts I'll just have to say. So 2 facts. One is that this works. Is that you get the same. You can do this on any manifold. Okay, so this is what goes on in a geometry class. In geometry class, we try and teach you what happens, not if you're just looking at RD, but you're looking at some d-dimensional curve, shape of some kind, which locally looks like RD, but it could be a sphere, it could be a torus, it could be something much more complicated. But the point is that, so M is some gadget which locally looks like RD, and where you can choose local coordinates so that this whole story works. And then then you just have to, a more interesting manifold, you're going to have to use several different coordinate patches on it. And you're going to have to make sure that all the structures you work with, kind of when you go from one coordinate patch to the other, that they behave in a nice way. That if you change everything is behaving consistently under coordinate changes, so that it doesn't matter which coordinate patches are using, or you've got some global object. So that's what. So this is so you get what's called. So this is called the differential forms on a space. Okay, now the interesting fact is that there exist operators. There's a d such that omega k of m goes to omega k plus 1 of m. And okay, and then delta, so omega k of m goes to omega k minus 1 of m. Okay. So the other story that if you study this theory, what you'll find is that there's something called the Durand differential, which takes k forms, things where you've got k of these, and it moves you up to things where you have k plus 1 of them. Okay, so this is the B, and this you can write down even without a metric on the space. You can have a notion of a space with coordinates in a space, but no notion of distance on it, and you can still have a D. If you do have a notion of distance, if you do have a metric, then you can take. There's kind of an adjoint. You can take an adjoint with respect to the natural inner product on these guys, and it's your delta. And what you have here then is okay. Yeah. And you have d squared is equal to 0. So the interesting thing about this operator D is that its square is 0, and you also have delta squared is equal to 0, and then you have D plus delta squared is then equal to d delta plus delta d, and so this is an operator which, so the degree goes down by 1 and then up by 1, so it stays the same, and here it goes up by 1 and down by 1. So this takes omega k of m, omega k of m, and it's actually equal to the Laplacian. You know, that's 2 k. Okay. So you get a so each of these guys have derivatives that have derivatives embedded in them in the bosonic piece, and then in the fermionic piece they're increasing or decreasing the fermionic degree by 1. But it's a second, as a differential operator for the bosonic pieces, it's a second order differential operator, and it really is, it's the natural, it really is the Laplacian. And so this tells you, for k is equal to 0, it's just that functions is the Laplacian. For arbitrary degree, you've got a Laplacian on forms. And then so what you found here then is that and this is kind of one of the important facts. So the Laplacian, so Laplacian is a square, is a perfect square. And you get the same. Yeah, it's a perfect square. And so what you're really doing here, this really is this is an example of a supersymmetric quantum mechanics with the Hamiltonian. Hamiltonian is equal to d plus delta squared, on the space. Well, which I'll say that the forms on M. But if M were RD, this would just be L2 of RD times lambda star CD. Okay, so the so this kind of weirdo quantum mechanical object that a quantum mechanical system that we've created, and this weirdo notion of supersymmetry, it actually does have have a very well-known corresponding object in mathematics, and it's exactly the story that you get the story that happens when you try and do geometry and use differential forms. And then the new structures that appear in geometry when you do differential forms and you use the Laplacian and you use the fact that it's a perfect square, these are things that are called Hodge theory. So this is something you normally don't get to in a first course in geometry, but So in first courses of geometry, typically what you're doing is you're just talking about, you define differential forms, you define what D is, and then maybe you start talking about metrics and about delta, but this whole business about what happens here, but then you're going to have the same question becomes interesting of, are there solutions? So are there, how? So there's the basic question of how many solutions to D plus delta, psi, times a differential form, which I'll call it omega. So this is are there. And it turns out that this has the answer depends upon the it depends, and it's basically something. It depends on the topology of M. Okay. So one reason people are interested in the Dirac and differential forms and the Dirac operator and all this stuff is that if you got some manifold and you want to know about its topology, how many holes does it have in it? You know, does it look like a sphere? Does it look like a donut? Well, you can figure that out by looking by counting the solutions to this equation. You know, and it's similar. So it's similar to what I was trying to do in supersymmetric quantum mechanics. And so I can just stop there. But maybe then historically, I mean, this kind of analogy between supersymmetric quantum mechanics and Hodge theory. This was kind of, it was first really discovered and first really investigated by Witten in the early 80s. And it really, the fact that you could write down a quantum system, and that the answer to a basic question about it, like how many ground states does it have, was given by a question about the topology of some space. This was kind of the founding idea of what's become kind of topological quantum field theory. So these are kind of the simplest. This is really the simplest example of what's called, you know, what's become this huge subject of topological quantum field theory. So anyway, sorry if you haven't seen differential forms and this D operator, this would be pretty mysterious. But it's actually, you know, if your manifold is just RD, it's just exactly the thing that we've been playing with and what we've already written down. You know exactly how you already know what D and delta are. They're just Q plus and Q minus. But if you have to know some geometry to know what to do if you've got a space which is patched together out of RDs. Okay, I think I better stop there now. But any questions? Yeah.
Like question on deltas. So I know B, like we could see it as like partial with respect to the local coordinate chart, and then wedge product with another D.
Yeah.
DFA. How is the delta defined? Like I'm not sure how it can reduce the.
It's going to be something like. Well, so you're saying D is going to be some sum over J, D, dxj, and then there's a dxj wedge operator. Yeah, and so delta is going to be something. The problem, then you get into various problems. Now you've got problems with signs and all sorts of things, but it's going to be something more. It's also going to have the ddxj. But it's going to be something more like interior product.
First, you have to deal with orientable manifold.
Yeah, there's. I mean, this one is relatively easy to write. The point, I mean, the abstract point is that this guy, you know, if you have a metric, then you have an inner product on differential forms. If you have two differential forms, there's an inner product which is given by by integrating over the manifold, the differential form wedged with the Hodge star of its dual. Anyway, there's a long story here, but the abstract thing is that this is there is an inner product on differential forms if you have a metric on the space. So if you have a metric on the space and so can define a Hodge star, then there's you can write down. There's a nice idea of what the inner product is, generating just the integral of one function type of function. Anyway, and you may if they're complex, you may want to put a bar there. But anyway, but this guy is just this guy abstractly is the adjoint operator to this guy with respect to this inner product. But you know, if you try and write him down in coordinates again, I think they're also going to be well. And the adjoint of this guy is going to be some kind of contraction operator, some sum over contraction operators. But I don't. But this guy's always harder to write down because he depends on the metric. So I don't want to.
Yeah, but you can also write it down as plus or minus star D star.
Oh, I see. Yeah. Oh, that's right. Yeah. So if you have if you have the star, yeah, then you can write delta as, what is it, star d star or something like that. Yeah, that will give you the adjoint. But then there's sign
Or
problems.
maybe sometimes there is a minus sign depending on the degree.
Yeah. I mean, there's a lot of, anyway, partly because the signs you get depend on how you multiply things. There's a lot of tricky signs to deal with in all of this. But there's a lot of things that I think I really shouldn't try to, I shouldn't really try. I'm afraid I really should tell you, you got to go look this up in a book where somebody does it properly, because it's, if I just try to write it down, I get quickly into too much technology. But it really is just the adjoint, and you can write down the adjoint various ways once you know the metric, and knowing the metric is equivalent to knowing the Hodge star operator. But I haven't told you what the Hodge star operator is, so.
At least intuitively, so you're saying we're given like the n form, we're just contracting pairs of like what the delta operator is doing is that we're contracting pairs of like the xj to be the same index, such that we're reducing it to a n form.
It has to take a k form and give you a k-1 form, so it has to kill off these guys. But I think, I think maybe it's important to say that these operators, this d operator, this is not an intuitive object. I mean, this is not something, if when you took a course, this was a completely obvious guy and it was exactly clear to you everything it was going to do, you probably were misunderstanding things, because this is a very mysterious object. I mean, the fact that differential forms exist and they have this d operator on them that squares to 0 and tells you all about the topology of the manifold is really kind of an amazing. It's not an intuitive fact. It really isn't. It really is a very deep fact about how geometry and topology work at a deep level. And this guy is a bit more of a subtle object, because he really depends upon the metric. The interesting thing about this guy is that he's really kind of topological. He's really invariant under all coordinate transformations. He doesn't actually know he doesn't actually care what the metric is, whereas this guy really does. So this guy, I don't know. I find it best to think of this guy really as just once you have a metric, this guy now has an adjoint, and he's this guy. But neither this d or this delta are really they're not really intuitive gadgets. And but these are exactly our q plus and our, well, I think which is which. Yeah. Anyway, I think one of these is q plus, and one is q minus, or one is q plus plus q minus. Anyway, on RD, these are exactly our q plus and q minuses. So, and there on RD, you have this kind of weird superalgebra story about that. You've got these degrees of freedom which are fermionic, which are anti-commuting, and which are there isn't something in your brain which kind of makes this a natural story. It really it's something that takes some getting used to, but it is kind of a deep fact about geometry, and also about the relationship between geometry and quantum mechanics, I think. Okay.
And the reason why, like we're saying that the d delta plus delta d is a generalization of Laplacian is that, like, can I think of it like it expressed in terms of local coordinates? As again, it's just the partials, the double partial derivative on each of the components.
So it should basically come down to d delta plus delta d. It's going to be it's going to be essentially the sum over j d dx j. But remember, it's also it's just going to be the second derivative operator. So it's going to have some fermionic stuff which takes you up a degree and then back down. but as far as the derivatives are concerned, it's really in local coordinates. It's just going to be the second derivative. It's going to be the standard kind of invariant combination of the second derivatives. Yeah.
So in the lowest energy level, how is the Laplace related with the Casimir?
Well, okay. Let me
In the lowest energy, for example, in like.
Okay, so let me talk about next time what I'm going to do, what I want to do next, and I think now I won't do what I told you at the beginning. Let me go on to the Dirac equation next time. So in some sense, yeah. So this is one story, but this is really kind of. This is kind of a nice fermionic generalization of the harmonic oscillator story. If I want a fermionic generalization of the free particle story, of the free particle, then I get something a bit different. And that's what I'm going to talk about next time. And that's where you're going to get the Casimir operator for the Euclidean group has a square root, and then that's going to be given by the Dirac operator, but we'll talk about that. That's a separate story here. Yeah. So here there's no Yeah. So that is related to this, but it's a. Well, I guess it's true. You do actually have a It's true. Yeah. You do actually have a Casimir. You do have a Casimir. So there is this Laplacian on forms is kind of a Casimir operator, and you've got a square root of it. But it's the problem is what you're doing here is you're acting on all differential forms. So from the point of view of physics, what you're doing is you're taking your state. You're taking, if you try and think of this as a free particle system, you're taking you're taking wave functions which take values in all the antisymmetric tensors. So it's not just a anyway. And I tried to say that you would maybe I should. This is getting a little bit too complicated, but I tried to analyze the way the Euclidean group acted and said that and say that okay, it's going to act on these things and they're going to be labeled by this helicity, right? And in two dimensions, yeah, by the helicity. And what I'm going to talk about next time is how to construct the the helicity plus or minus 1/2 kind of spin representations of the Euclidean group, and how to think of and to show that in that case your Hamiltonian operator, which is the free particle Hamiltonian, has a square root. But here you're operating on all differential forms at once. And so from the point of view of what I'm going to talk about next time, yes, there is a Casimir, and yes, it has a square root, but what you're acting on is things with all possible helicities from 0 up to D. And I mean, you've got all these antisymmetric tensors you're operating on. So you're operating on something kind of complicated. Anyway, yeah, I don't know if that helps, but next time we'll go back to something simpler. But we'll go back to just to 3 dimensions, and very explicitly study the free particle system, with a spin coupled to a spin 1/2 degree of freedom in 3 dimensions, and show that there, again, the Hamiltonian, which is just p squared over 2m kind of thing, that has a square root, and it has a square root where and to understand that square root, you have to understand these fermionic degrees of freedom, and that square root you can generalize to any dimension, and it's going to be called the Dirac operator. But I guess maybe the thing just to watch out for is that this is not. Maybe I'll say so. The subtle thing is this is not the Dirac operator. Okay, this is the square root of. Anyway, because the Dirac operator acts on spinors. This guy acts on all anti-symmetric tensors. Okay, so I don't know. Anyway, I'll say, maybe I'll say I'll maybe say a bit more about the relationship between this and the Dirac operator once I define the Dirac operator. So, anything else? Okay, that's it. So I'll see you again on Thursday, and again I'll be here for a while. So if you have any questions, just connect to the other Zoom thing. Okay. Okay. Bye now.
Yeah.